Hi, I'm Natasha. For my final year master's project at Imperial College London, I developed a lifecycle analysis tool. This tool was designed to conduct and automate lifecycle assessments for aerospace composites such as carbon fiber and glass fiber. In a nutshell, this tool acts like an AI agent where you can feed engineering-based questions such as calculate the environmental impact of a certain material, and the agent responds with a well-cited, calculated, and a deterministic answer every single time. But before we delve any deeper into this, let's address the elephant in the room. What exactly is lifecycle assessment? Well, lifecycle assessment, or LCA if you may, is how we measure the true environmental cost of a material. It's not just about how much it weighs, but also how much energy was consumed or how much carbon dioxide or other greenhouse gases were emitted during the production of the material, and what happens at the end of its life. The problem is that traditional LCA tools are complex, static, slow, and often expert dependent. This isn't ideal for rapid early-stage design decisions. If you ask a general-purpose AI model for LCA data, more often than not, it's likely to make things up. In other words, data hallucination. My LCA agent fixes these issues. This is the landing page where the user can enter their queries into the chat section below. I built this tool using Daisy, which is Imperial College's own GenAI platform. At its core, the LCA tool is a retrieval augmented generation-based agent built using OpenAI's GPT 4.1. And this just means that rather than relying on the model's training data, which may be outdated or even inaccurate, the LCA agent searches a curated lifecycle inventory database that I built using over 50 different peer-reviewed sources, industry databases, and environmental product declarations. The LCA agent ensures that every answer it gives is grounded in the database and traceable to a source. In theory, zero temperature and top P values would enforce determinism. However, based on some of the tests that I conducted, I actually observed that a zero temperature and zero top P led to the LCA agent's responses being stuck in syntactic loops and often failed to fully articulate the complex multi-step chain of thought reasoning required. The temperature of an AI model is an example of a hyperparameter that controls the randomness of its predictions. Similarly, the top P restricts the probability of the tokens that the model can consider. So in order to allow more flexibility in the agent's responses, I increased the temperature and top P just slightly above the absolute 0 to 0.1. And at this configuration, I also achieved the highest exact match accuracy. And this temperature and top P configuration ensures that the LCA agent's outputs are deterministic. Ask it the same question 30 times, you get the same answer every single time. Now, let me walk you through 5 test cases to show you exactly what it can do. The first test is perhaps the most fundamental one. It tests whether the agent knows what it knows, and does it refuse to make things up. I am now going to query the agent regarding the energy and emissions metric associated with building a bulkhead using Kevlar and carbon fiber. The database contains information for carbon fiber, but not for Kevlar. Now, let's look at the response being generated. For Kevlar, the agent has explicitly specified that the data is missing from the internal database and whether the user will like an estimate. And there you go. As you can see, it didn't make something up. Most general-purpose AI models would confidently fabricate a number here to satisfy the user's request. However, the LCA agent refuses to give a response outside its verified data, and it also tells you why. Let's also look at the carbon fiber result. The LCA agent has correctly extracted the relevant energy and emissions metric from its database and also traced it back to the primary literature. I am now also asking the LCA tool to proceed with an estimate for the information that was missing for Kevlar. As you can see, it only generated a response for the missing information when it was authorized to do so. Crucially, it labeled the unverified numbers as an estimate and also advised the user to not use the estimated numbers for formal LCA reporting. And that's a foundation, grounded, cited, and honest about its limits. The second test case tests for something a little more subtle, specifically the system boundary. I'm now asking the agent to find the difference between the global warming potential, which is the emission metric I used, between an intermediate production process and the finished carbon fiber. And once again, the agent has correctly retrieved the relevant information from its database for the intermediate and the finished fiber. It also calculated the difference between the two numbers and also justified the difference arising due to the downstream processing and conversion steps in the manufacturing chain. And that kind of a phase-level breakdown is exactly what an engineer needs when deciding where in the supply chain to intervene. Now let's stress test the maths. Real manufacturing does not work in clean, round numbers. Instead, there's always adjustments that need to be made, such as incorporating the scrap rate or the regional energy grid mix. So let's see how that affects LTA results in practice. I am now asking the LTA agent to calculate the true energy consumption as quantified by the cumulative energy demand when just over 9% of the raw input mass is wasted during production. From the response being generated, you can see how the LTA agent has calculated the true input mass required and therefore the overall energy consumption. I also cross-validated the numerical outputs against OpenLTA, which is one of the industry standard LTA software. Zero deviation, identical output, and the same number, though arrived independently, through a natural language query. The fourth test I designed specifically to catch the agent out. This is because this is a leading question with a false premise, so let's see how the LTA agent responds. I am now questioning the LTA tool whether glass fiber is always the better environmental choice for transport vehicles from a lifecycle perspective. So, according to the numbers, glass fiber does look better on paper. By those numbers alone, glass fiber wins easily. But the LTA agent doesn't just stop there. It flags how glass fiber is almost 1.5 times heavier than carbon fiber for equivalent tensile strength. In weight-sensitive applications such as in aerospace, you would need more glass fiber. And this density penalty can completely offset the lower per kilogram emissions that was earlier achieved during the manufacturing process, compared with the higher emissions in the use phase. In conclusion, glass fiber may not always be the optimal environmental choice. The real answer largely depends on the vehicle, the use case, the lifespan, and also the structural requirements. And that's not just retrieval, that's an added analytical reasoning capability. And the LTA agent cited every number it used to get there. Here I asked the agent to conduct a live web search to find if there are any recent factory closures that might affect the supply chain stability of manufacturing glass fiber in the UK. Since the agent is now searching beyond its internal database, it does take slightly longer to generate its response. However, this is still within a minute, so still commendable. After conducting its web search, the LTA agent has correctly retrieved and synthesized the event, stating the closure of the UK's largest glass fiber factory in 2025, and factors this information into its supply chain risk assessment, therefore ranking the supply chain stability as low. One thing that's worth mentioning is that the LTA agent only used the approved journalistic domains that it was allowed to search for its web retrieval that I specified when constructing the LTA tool. And this is where it stops being a simply static LTA tool and starts to become something more. A live engineering intelligence layer that connects material-level environmental data to the real-world geopolitical and supply chain context. And now let's discuss the performance metrics. Starting off with the semantic relativeness, which scored 85%. This means that despite of any variations in the wording of its responses across multiple iterations, they were generally linguistically coherent with the ground truth. Next, the factual accuracy metric scored 96%. This number implies that the LTA agent's responses were almost always factually correct. And finally, its best performance. The faithfulness score came in at 100%, proving that the LTA agent was completely faithful to its internal database and none of its responses were ever fabricated. To summarize the validation, across multiple simulation runs, the LTA agent produced identical outputs at every single iteration, also quantified by a 0% coefficient of variation. The LTA agent also deviated by 0% from the OpenLTA calculations, indicating the accuracy in its mathematical results. I replicated the LTA study for both carbon fiber and glass fiber on OpenLTA. Here I only go through the results for the carbon fiber test. However, the overall conclusion from both the tests were essentially the same. For identical inputs, the LTA tool and OpenLTA return the same values. And this just proves that the LTA tool's calculations are not just reproducible, but also mathematically correct. And of course, the LTE tool comes with the added benefit that it streamlines the long and manual processing required on OpenLTE. And for its most immediate deployment, the LTE tool would work well in conjunction with OpenLTE or other traditional LTE software rather than as a standalone replacement. And that's not a coincidence, that's the architecture working as designed. You may be wondering, can you not just use a general purpose AI model? Well, I went ahead and conducted this test for you. Let's begin with the general unconstrained AI model. In the first run, it behaved as expected. Since it did not have an assigned database, it asked for more information. But across runs 2 and 3, it generated very different responses, and this clearly exhibits the stochastic and unstable nature of general AI models that are often prone to data hallucination. On the other hand, the LTE tool returned the same number every time with full citation. This shows that even though both tools use the same base model, the previously unstable and probabilistic AI model became more reliable and traceable through proper architectural constraints and training. At this stage, this LTE tool is still just a proof of concept, but it does point to something real. The idea that domain-specific constrained AI agents can make expert-level engineering workflows accessible, fast, and reliable. However, there's still a long way to go. Whether that includes conducting prospective LTAs or supporting multi-material trade-off studies, or having a multi-agentic architecture, or even live API integration. But as a foundation, I think it shows what's possible when you stop asking a general-purpose AI model to guess and instead start building something using a tool that knows what it's supposed to do. If you've got any questions, thoughts, or if you're working on something similar, I would love to connect. I will add the link to my LinkedIn profile in the description below. Thanks a lot for watching today.